The notion of function of random variables involve a topic of having the random variable x that distributed as fx. It has its own distribution. And this random variable x is applied under the transformation g. It can be anything, can be linear or nonlinear. So it gives the output y that is certainly going to be another random variable. So the question is, under the transformation g that will transform x in many ways. Uh, what can we say about the transformation? Sorry, about the distribution of y? How does it look like? Of course, we conceptually the distribution of y should depends on fx and also should depends on the nonlinear transformation g. So in this video, we give you a few examples, some well-known transformation. For example, quadratic function. For example, ReLU function, or the positive thresholding. And we give you a generalized result that for any nonlinear transformation G, how can we derive the distribution of y as the expression of distribution of x, and also somehow there's going to be some information of g included in that formula. So the setting is the following. Suppose we have a random variable x and let g be real value function that defines on the real line. So in this case, we talk about x and y that are both takes that they both take real value. So y equals gx, y is also a random variable. As I said earlier, the CDF of y depends on g and depends on the distribution of x. For example, the ReLU or half-wave rectifier, this notation says that you're going to take only the positive part of x when x is greater than 0, and it gives you 0 when x is negative. we have these example all the time in engineering applications. Suppose a signal x is according to this one, and it take both positive and negative value. So after apply this function, it's just gonna flip the signal on the positive y-axis. Okay. Um, you can see similar, you can see this positive thresholding transformation in this example, in this setting, that we have uh, we have active speakers. Suppose we have a number of speakers as in input x, and this is so you have voice transmission system, and because of the voice transmission system has a limitation, it can only carry m speakers at a time. So the output, so suppose you have the input x, and this can be maximum as m speakers that you can release at the output. So you can represent y as a function in x as x minus m, um, and this is positive thresholding. So it means that it can only carry the active speakers up to m speakers. So the whole concept of deriving the new distribution of y in terms of x relies on one concept, one idea, that when you have when you have two equivalent events as a set, for example, if set if set C if two sets are equivalent or they are equal, so the probability of those two events must be equal. So whenever y that lies in the set C, okay, if you can derive that equivalent to uh of course y equals gx, all right. So whenever y is lies in the set C, and that's of course gx lies in the set C, and when somehow you can convert that when gx is in C, that's equivalent to that's equivalent to x lies in some set B. So in when once we get that, we can conclude that those two probabilities must be the same. So like using this concept, so what we're gonna start is the left hand side. We're gonna start by the requirement. So we're gonna start by say that something like y is less than a dummy variable small y, because these give you the CDF of y, right? And then somehow using information about the nonlinear transformation G, we're gonna derive that, okay, this event is equivalent to x lies in some set B, all right? So once we get that, we can write this as some CDF of x. It's going to be much clearer if we can explain this in on some simple example. Okay, let's talk about the previous example where you have x as the number of active speakers, and then these speakers, the voice that you talked through the speaker, will be transmitted to the transmission system. Okay, that you can think of this as some nonlinear function x. um okay, I think my window just covered my writing. Okay, okay, this is a transmission system. And then because of the setting that the voices transmission system can transmit up to m signal. So when the number of active speaker exceeds m, the output y can only send m speakers. Okay, this is the output y. So we can write this relationship as y, because y is going to be the number of signal discarded. So y is going to be x minus m, with the thresholding, the positive part of x minus m. Okay. So when we derive a certain random variable, uh, uh, the very first thing is you should derive, or you should elaborate the sample space of that variable. So if we let y to be the number of signal discarded, all right, y can take the value from 0, 1, dot, dot, dot to n minus m. Okay. Think about the first case. Y could be 0. Y could be 0 when x is less than m. X is less than or equal to m, right? And y could take the value of n minus m when this is when x is, I mean, when y can take a value from 1 to big N minus big M. That's the case where x is greater than m. So we can derive the PMF of y for each case. So think about y when y could be 0. The probability of y is 0 is, of course, when x is less than or equal to m. So now we lie down that x could be any positive integer from 0 to m. Okay, this is step where I said that you start from the probability of y and you try to derive that probability that is equivalent in the events of the variable x. From here to here, you can see that you use the information about gx. Mhm. And the rest of the process is just follow from this, all right? What is the prop of x in this set is simply the sum of PMF in x from 0 to m. When y is 0, dot, 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 n minus m, or this is when you can think of the equivalent event that this is when x is bigger than m, right? So there's going to be excess. So when x is greater than m, you can write that, oh, x is m plus k, and that is the variable k, the number of k, the value of k is of course is the value of random variable y. From here, from here to here, you use the information about G, and the rest is, of course, what is P of X equals M plus K? That is PMF in X at the value M plus K. And K takes a value excluding 0, but K is less than or equal to big N minus big M, N minus M. Okay, this is it, right? This is how you derive. So you arriving at the expression of PMF of y, but your PMF of y splits into two cases, when y is equal to 0 and when y is greater than 0. Now let's take a look at another example where the random variable takes a value on a continuous interval. Now, in this example, we have such a well-known and very common that is affine function y equals ax plus b. And in this case, let's assume that a is positive just to simplify the calculation. The question is very simple. Under this affine transformation, can we derive the distribution of y in terms of the distribution of x? Now, the concept goes the same way. Um, we're gonna derive the two probabilities that are equivalent. Thinking about think about how to get a distribution of y. Of course, in order to derive the distribution of a certain variable, knowing density or knowing CDF are the same thing. Because PDF, small f, and CDFs, these form a unique pair. So I'm gonna start with um, CDF in Y, because I know that if I start from having CDF in Y, I can get back to PDF later, because by taking the derivative of big F, I will get a small f, the PDF. Okay, this is a CDF of Y. Let's now the next step is, this is a probability of the events in Y. We're going to derive an equivalent probability, but in terms of the variable x, by using the using the information of the transformation. And when y is less than y is less than small y, you can say that you can just simply say that, oh, this is a prop of ax plus b less than y. And from this step, you still try to find the equivalent prop. You just flip, work around with this inequality. And this is why we assume a is bigger than 0 first, because this is just to simplify. You know that when you derive the inequality, the side of a is important. So now we flipped x like this, and what we have is the equivalent path in terms of x. This is actually the CDF of x at y minus b over a, because this is just a dummy variable. By the definition of CDF, this is CDF of x at this value. Okay. Now what you get is that you get CDF of y expressed by the CDF of x, but the dummy variable now is in terms of y. In order to get the PDF, we can simply take the derivative respect to y. Now you see that you're going to apply the change rule. If y is df big F by dy. So that's going to be fx prime. Let me just say it explicitly. So you're going to derivative fx y minus b over a times the chain rule. This is the composite function. It's a composite of fx with 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 this linear function. So this is going to be multiplied with the derivative of this guy with respect to a, which is 1 over a. And because the derivative of CDF is PDF, and this is what you get, so you're going to get small f PDF times 1 over a. Now we have arrived at this nice general formula. Whenever you have affine transformation in X, where the coefficient is positive, what you can do is that you just look up the PDF function of X, evaluate it at y minus b over a, and scale by ya. We're going to come back to this affine transformation again and derive the PDF and y using another tool, using transformation method like characteristic function. But this example just illustrate how you can derive it um, using the analysis of having two equivalent probabilities. Next example is the application of this. When you have affine transformation, you have this nice formula in the green box. How about applying this result to the well-known Gaussian example? In this example, the setting is that we have normal x that distributed at normal with mean m with a variance of sigma square. We know that the distribution of x is given by this. The question is, if I transform x with affine transformation according to this coefficient a and translation term in b, what is the PDF of y? Okay, let me just write down the formula from the previous page again. This is the formula from the green box. Okay, so the application is just directly put all the ingredients in the formula. So if y is equal to this, okay, now let's just evaluate f x y minus b of a. So that's a very simple. So you get 1 over this e to the minus y minus b over a minus m square to sigma square. And once you get it in, it's not hard to see that this is going to be the expression of the density in y. And now from this step, this is what you get. Prior to deriving this, you don't know which distribution of y, right? You just know that y is an affine transformation. But after you arrive at the density of y, you take a look at the form and you see that, oh, this form of PDF is also a class of Gaussian. And you can read the mean and the variance of the Gaussian from this term. Now what you can do is that, oh, I can read that the mean is shifted to b plus am, and I can read that the variance is now a sigma the whole thing square. Therefore, from this result, a linear function of Gaussian is also a Gaussian. This information where you can read the mean and the variance of the Gaussian from the expression of PDF also agree with the fact that when you have affine transformation, the at least two moments that you can conclude without knowing the whole distribution is that you know that EY is gonna propagate by the affine transformation the same way we have here. And we know that this is what we know prior, that uh, uh, that the variance of y depends on the coefficient of a squared. This is what we know in an another independent analysis. But I want you to take a look that O is also agree after we read off the mean and the variance of the Gaussian distribution that we concluded from this analysis. Okay. Next, let's take a look at quadratic function. Quadratic function is also found a lot in applications because quadratic function represents something as power or energy. You have that power that absorbed by a resistor in the circuit as the current square R, right? Also V square over R, okay? The energy of a lot of entities in the physical real world, energy and power are two related concept, right? We have kinetic energy that is a quadratic function. Let me write it down here. Kinetic energy that is a square function of velocity. You have potential energy that absorbed by a spring that is stretched by a distance x as 1/2 kx squared. So a lot of physical quantities in this real world has a quadratic function expression. So the question is the same. If I have a random variable x distributed as fx, what's gonna be the distribution of y? Okay. Obviously, according to this transformation, you know that y takes non-negative values only. Okay, so I'm going to derive equivalent event. I'm going to start with y less than small y because I know that I am going to derive the CDF in y first. That's why I'm interested in this event. But when my y less than small y, this is my small y. So I take kind of taking the inverse of the transformation g, and now I look at the x-axis. This is going to be minus square root y. This is going to be square root y, right? So I have derived that when my big Y less than small y, my big X, my random variable X must lie in this interval. Therefore, I can sketch down my CDF. My CDF of y would be always 0 if y is negative, because that's not gonna happen for sure. My CDF in y, my CDF in y at small y is gonna be the probability of this, all right? Probability of x lies between left and right. You know that when pop of x is less than a less than b, that is fb minus fa. So I get this expression, and the rest is the same. You have derived CDF of y as a function of as the expression of CDF in x, but with dummy variable small y. To get PDF of y, you take the derivative respect to y. And now again, you need the chain rule, because again, this is composite function of fx with square root function in y. So you take the derivative of fx, you get small f. You take derivative of square root y, you get 1/2 square root y, 1 over square root y. And this is the second term, and with the sign thing, and this is the answer. Okay, you got actually what you get here is another general formula when g is a quadratic function. To apply this result, how about this question? This green box gives me a general result that whatever input that x goes in, the distribution of y is distributed according to this green box formula. But now let's apply to a special case when x is standard normal. When x is standard normal, what is fx? Is gonna be 1 over square root 2 pi e to the minus x squared half. Okay. So if you just plug those in, I believe it's not that hard. Okay. Do I have space? Okay. Nah. if I plug that in, fx square root y is going to be this, right? Okay. If I put 2 square root y, that's gonna be 2 square root y. Okay. But when I add the second term, the minus square root y, when it goes in this function, it gives you the same, this is going to be the same expression as this. So at the end, if y is for when x is standard normal, that's going to be 1 over square root 2 pi times square root y e to the minus y half. Okay. And it turns out, if we take a look at this expression, it turns out to be chi-square random variable with 1 degree of freedom. You can take a look at this and go to the general expression of chi-square random variable. See if it match for uh, degree of freedom 1. After we have seen these 3 examples, I would like to uh, take a look at this problem again conceptually and see whether we can derive a general formula for any transformation G. Um, it turns out that, yeah, that we can under some assumption. Now we take a look at y as a function of x, and this G can be, doesn't have to be 1 to 1, it can be many to 1. Which means that when our values of y is given, we can solve this equation, we can solve x in terms of y, and that can have many roots. And suppose that we have n roots, and that's what we mean by many to one function. For example, if y is given is here, this is the first root, this is the second root, this is so on, third root. Okay. Now we're going to derive 2 equivalent events. Now let's take a look at this graph closely. If I perturb y a little by dy, okay, of course you're gonna see some perturbation of the roots xk by dxk. Okay. Now if I derive the interval that my y is between this interval, that's gonna be equivalent to the set of equivalent events in the yellow intervals. All right. What it means is that whenever my y lies in this interval, that's equivalent to my x lies in this interval or this interval or this interval. Okay. So in terms of the set, we express by this. This if equivalent to the union of the yellow intervals. Okay. And recall that I'm going to derive the probability of this, and that's equal to probability of this. But the pop of this is the density times dy. Okay, we can approximate it that the prop of this is the density times the perturbation times the size of this perturbation dy. And remember that when we have the pop of set of A union set B union set C, and whenever this set is mutually exclusive, they don't overlap. All right. So the pop is going to be the sum of the probabilities. So that's why on the right hand side, the sum of this pop is the density at fx, the density of x at x1. So the density times the size of the x1 and so on. Okay. And what we're gonna do is that because you wanna derive fy, you're gonna move these around to the denominator, to the denominator, to the denominator. So you're gonna have each of the term that looks like this. And because y is gx, all right, this y, this given y is a output value of the function g at each of the roots xk. So dy by dx is simply the g prime by our notation, the g prime of x, and evaluate at xk. And that's why this expression is expressed like this. It's actually the Jacobian, the derivative, all right? Jacobian or derivative of g evaluate at x1 dot 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 until xk. And that's gonna give us a general formula for any distribution f for any transformation g that is a real value function. Uh, with this general formula, we can verify. We can use this one, but with the previous example, and verify that the results are the same. Okay. When when g is affine, the derivative is very simple. It's a, all right. And the next step is you have to solve for the n roots. But for affine function, is one-to-one mapping, so it has only one solution. Whenever y is ax plus b, you can solve. You can take the root that x is y minus b over a. Okay, and you just plug it in because it has only one root, right? According to this formula. So you just plug it in. It's going to be fx y minus b. And because of this, this is going to be the magnitude, all right, the absolute value of the Jacobian. So when the Jacobian is a, you get the magnitude, the absolute value of a. With the previous quadratic function, now I put a general coefficient in the quadratic form whenever a is positive, all right? You know that first, let's talk about the range or the sample space of y. When a is positive, certainly y cannot be negative, okay? So we can rule out that when y is negative, the density must be 0. This is kind of deriving the support of y, like taking the when y is positive, you're gonna solve for the roots of this quadratic equation. So it has two roots when y is positive, so it's one root and the negative root. So now your your formula is gonna go like this. It has two roots, right? It has two roots, so you're gonna have two terms on the right hand side. And I think the rest is just to substitute this, directly, very straightforward. So x1 is square root of y over a. X2 is negative root, and that's it. So for the Jacobian, g prime x is 2ax, but your root x1 is y over a, and that gives you 2 root a y. And you just plug it in, and this is the result. So this result is general in the sense that this is for any quadratic function that have positive coefficient. If a is negative, I think it's not hard to derive this using the general result. Okay. Last example, not last one. Okay, second to the last one. The log of uniform variables. Suppose we have we have x that is standard uniform in the interval of 0 and 1, and y is negative log x divided by a positive constant lambda. What we're gonna show by this analysis that it turns out that my y is going to be exponential distribution with parameter lambda. Okay, so let's prove it. Um, the function log x is this way, so negative log x is gonna look like this way, right? So this is interval of x, this is y. So whenever x is between 0 and 1, your y takes a positive value. This sorry, this function, this log function, negative log function is one-to-one mapping. So whenever big Y is small y, you can solve for the root. You can solve back. You can write x in terms of y, that x is exponential negative lambda y. It is unique root. Um, so the formula is gonna be according to the result, right? What I did is that what I'm gonna do is that I'm just gonna apply this general result. So we solve for the root x1, suppose, because in this example it has only one root. Okay. Um, for for the root is e to the minus lambda y, right? And let's find the Jacobian. When you take the Jacobian, what is g prime? My gx is negative log x over lambda. So when I take derivative of log, I get what is the derivative of log is 1 over x, right? So I get minus 1 over lambda x. And then I'm gonna, because I need to evaluate the Jacobian at the root x1, but my root is e to the minus lambda y. So I plug this in and I get this expression. Okay. Now, when we have all the ingredients ready, now let's clarify the density function in a proper way. Whenever y is negative, that is not possible. The density of y in that case must be 0. When y is positive, is non-negative, right? Um, is non-negative. Um, that means when your roots lies in these 0 and 1, so we will have if x, okay, evaluate at x1, which is e to the minus lambda y, and the size and the magnitude of the Jacobian is this, which is you just plug in this expression in. Okay, now let's take a look at this term f x. This is the distribution of uniform distribution in the interval of 0 and 1. So this guy is constant, is actually constant of 1. All right. So that's why it turns out to be, the expressions turns out to be lambda e to the minus lambda y. And that is exactly the distribution of exponential random variable with parameter lambda. So the message that you could take from this slide is that when you have uniform, the negative log of uniform is exponential variable. Last example, um, you have um, you have a cosine, transformation, and your x is uniform in the interval of 0 to 2 pi. The question is the same. Under this transformation, what is the distribution of y? Whenever y is greater than 1, because y is cosine, that's not possible. In this case, the density is 0. When y is less than 1, we have to take the inverse of this function. And you know that when you take the inverse, you find the roots of this function. You have two roots. Okay, the first root is that, so x1 has a meaning of an angle. Is the cosine, is the arc cosine of y. All right, arc cosine of y. And because you know that in between 0 to 2 pi, all right, uh, eh, and because when you take the inverse of cosine in this interval, you know that you have two roots. The other root is 2 pi minus that angle. Okay, so this is the other root. So we can use this formula. Y is going to be fx x1 over g prime x1 plus fx, sorry, fx x2 over g prime x2. Okay. Now let's take a look at the Jacobian. When you take the derivative of cosine, you're going to get minus sine. At x1 minus sine of x1, sine, right? Oh, I think sine of x1 is going to be square root of 1 minus y square. And with the negative side goes here. Okay. And for the g prime of evaluate at x2, that is minus sine of x2, right? But minus sine of x2, so that's you go the same way. You take the sine of the angle of 2 pi minus x1. So the result is square root 1 minus square. So when you plug it in, so you're gonna plug this in, take the magnitude. But remember that on the denominator, fx x1, fx is uniform. So fx is, but it's a uniform in the interval of 0 to 2 pi. So that is 1 over 2 pi, 1 over 2 pi. Okay. So when you plug it in, everything, you're gonna get, I mean, these two terms are identical with the factor 1/2. So the sum of this is going to be 1 over pi square root 1 minus y squared. In the interval of y is between -1 and 1. You exclude you exclude um, the values of y equals plus and minus 1 because of the denominator. And that makes sense because we don't have to talk about the probability that because when y is continuous value, we don't talk about the probability that y exactly equals to some values, because the probability of that value must be 0 for continuous random variable. Okay, this is it for this topic. So the main message of this video is this slide. So please review.